were talking about hydrogen bonding last lecture, and we said in order to, technically, in order to get hydrogen bonding, we need to have two things. We need to have X, that we need to have H attached to X, and what's the X? It can be nitrogen, oxygen, or fluorine. And we need to have a Y, and Y is nitrogen, oxygen, or fluorine. And there must be a lone pair on Y. If you don't have a lone pair, there will be no hydrogen bonding, okay? Because you cannot share any electron with hydrogen. So there must be a lone pair located on one of those electronegative elements. We share it with hydrogen. Okay. And also I said hydrogen bonding is kind of it's really strong dipole technically interaction. But why do we call it hydrogen bonding? Okay. The reason for it, okay, you are not dealing with just partial negative and positive charges. Okay. You're not dealing with only like a permanent partial positive negative charges. You are dealing with a lone pair, one lone pair. And because you are dealing with two electrons sitting on fluorine, or let's say in this case, oxygen, and you're sharing it with hydrogen, that's going to be a strong intermolecular force. So instead of having just delta minus, we have a lone pair, we're sharing it with hydrogen. And that's the reason we call it, we call it with a unique name, and we say hydrogen bonding. Okay. Now, the hydrogen bonding, okay, hydrogen bonding, again, is subject to, how much positive or negative charges you're creating. The more hydrogen positive, the more hydrogen bonding you have, the stronger intermolecular force you will be dealing with. Okay, and I mentioned what's the meaning of protic, versus a protic solvent or molecule is the one that has hydrogen. The one that is polar but doesn't have hydrogen, we call it a protic solvent. Okay, now let's keep talking about the hydrogen bonding. So the more hydrogen bonding we have, the stronger intermolecular force we will be dealing with. Okay, boiling temperature. Right, so boiling temperature straight subject to intermolecular force. Okay, so first one, because it doesn't have a hydrogen, attached to nitrogen. Okay, it's not capable of creating hydrogen bonding. Yes, does have, okay, it does have like a lone pair, but there is no hydrogen. And next one, we do have lone pair on nitrogen, electronegative element, and hydrogen as well. Okay, and next one, we have all of them, but we got one more. Okay, one more hydrogen. Okay, so we have two hydrogen attached to nitrogen. So that means we have two places to make hydrogen bonding with two neighbor molecules. So instead of attaching just to one neighbor molecule, we can do hydrogen bonding with another one. Okay, and technically NH2 is capable of creating three hydrogen bonding, not just also two. And let me show you what I'm talking about. So if you have nitrogen attached to CH3, for example, okay, strongest force that you will be dealing with, it will be just technically dipole. Remember, this one goes up. You cannot cancel the force. Okay, you cannot cancel the force in that case. Okay, yes. And so we say this is going to be polar, and the strongest force, it will be dipole. Okay, but what will happen if I change one of the methyl with hydrogen? Okay, if you do that one, let's say you got lone pair here. Next, I'm going to put CH3 here. Okay, let's put hydrogen here, and then CH3 there. Okay, that lone pair, it can do interaction with hydrogen that's sitting on nitrogen, and of course here you have CH3, say CH3, and a lone pair there. So this is our lone pair. Okay, and that hydrogen also, it can have interaction with a lone pair from another molecule. Okay, and say we have CH3, hydrogen, CH3. Okay, so as you see, per one, per one lone pair and one hydrogen attached to nitrogen, we managed to get interaction with two neighbors. Okay, two neighbors. So what will happen if I replace another hydrogen, another methyl group? Okay, another methyl group with hydrogen. So right now I have one hydrogen bonding. Okay, forgive me, let's say highlight just this area. One hydrogen bonding. We're going to call this one hydrogen bonding, and the second hydrogen bonding, it will be here. So we have two of them. Okay, so we got two hydrogen bonding. Okay, let's copy paste that. Again, I'm going to change one of the methyl to hydrogen. Okay, so if I change one of methyl to hydrogen, let's say this one, we're going to change it to hydrogen. Okay, we're going to do the same thing here. Let's change that one, and for example, this one. So I put hydrogen here. Now I can have interaction with nitrogen that has a lone pair. And here we have hydrogen, and that CH3. Okay, so I managed to get the third hydrogen bonding. Okay, so technically one nitrogen with two hydrogens and a lone pair. is capable of generating 3 hydrogen bondings. The more hydrogen bondings you have, the higher boiling temperature you will be dealing with. So this molecule has a stronger hydrogen bonding. Okay, stronger hydrogen bonding than the one with only 1 hydrogen. But you have to be careful about one thing that we call it dispersion force. Okay, the molar mass of the molecule also is significant. You can't just simply ignore the molar mass. That is important. But hydrogen bonding here is playing a big role. Okay, you have 2 of them versus 1, so hydrogen bonding is going to be the dominant factor that you need to look for it. Okay, so the boiling temperature is when you don't have hydrogen bonding is 3.5. You have only 1 hydrogen bonding. Okay, 2 hydrogen bonding. You get 37, boiling temperature 37. Why do I say 2 hydrogen bonding? 1 with this hydrogen. Okay, so you can reach it from this direction, okay, through that hydrogen, or you can reach it through that lone pair. So you can actually get 2 hydrogen bondings. And if you replace with the second methyl group by hydrogen, the boiling temperature it will go up to 47. Okay, but the jump is not like from 3.7 to like 37, which is like 34-degree jump here. If you look at the jump here is somewhere around say like for example 10 there and 3, so we're talking 12. Okay, 12 degrees. Well, here it was technically 33.5 degrees. And why the jump is not that significant anymore? Okay, and one reason for it is like you can talk about the shape of the molecule also, and like how easy actually to make hydrogen bonding or make dispersion forces. I don't really want to go really in deep now, but like as you see, the jump is not that huge anymore. Okay. Hydrogen bonding, we deal with it in our daily life. And one place that I can mention, like whenever, or one way actually to make cheese, you take milk, regular milk, you can buy it from Walmart, and just simply add some vinegar with it, like when it's a bit warm, add vinegar to it, and like mix it, and very soon you will see, like if you let it to cool a bit, you will see that, like the technically the fat of it start to get attached to each other and they turn to insoluble fat, and you can filter it and collect that one, and that technically is your cheese. And if you wash it, and like if you will rinse it maybe a couple of times and then put it in like a mixer and add a bit, like let's say butter, and also just to get it like just to turn it to kind of like a creamy cheese, you can add a bit milk to it, and that's gonna technically it will be ready to use as a spreading, like a cheese. But if you take milk by itself and you heat the milk, okay, and then you let it cool, very soon you will see a layer of fat sitting on the top of that milk. It doesn't matter how energy you spend to get it dissolve or disappear like back inside the milk. That's not going to happen because the force that or the heat that you gave it messed with some of the intermolecular forces. Okay, and in this case we say we have a protein inside that milk, and that protein like it has a bunch of intermolecular forces. And in biochemistry you read about them as a primary, secondary, tertiary, or quaternary, structure of proteins. And that heat, it will break some of intermolecular forces, and maybe the helix structure or like the sum of those interaction between the sheets, the protein sheets will disappear. And because you lose that structure, your like the compound maybe it will not be soluble anymore, and that's the reason it cannot get back inside the milk. But one very well-known disease that technically it comes from from intermolecular forces is the sickle disease. Is the disease that the blood cell chain shape, their shape turned to be kind of like a sickle one, and because of that, their efficiency in carrying oxygen it will go down, and that person will suffer from kind of lack of oxygen. Okay, I want to actually start talking about that one, but before I introduce actually the disease, I want to talk about the last force that last intermolecular force that we need to cover, and that's going to be the dispersion force. Okay, and what's a dispersion force? Imagine you have a molecule. Okay, your molecule, I'm going to say CH3, CH3, CH2, CH3. Okay, so what do we have here? We have one group. Okay, that is identical to that one, and this is going to be the midpoint of the molecule. Okay, so that's going to be the midpoint. So I can highlight this one. Say that's the midpoint. Okay, now you can say, okay, the one on the right will pull to each side. Okay, so let's say we have a force here. Okay, that force is going this direction, and we're going to call it F1. Okay, we have equal force in opposite direction, and we're going to call that one F2. Okay, F1 is equal to F2. Okay, because they are 180 degrees from each other or cross of each other, they will cancel each other. So F1 plus F2 will be equal to 0. That means mu is going to be equal to 0. So this molecule is non polar, non-polar. Remember, you do have a CH bond, okay, and the CH bond is a polar bond, but the molecule C3H8 is non-polar. Okay, so the molecule is non-polar, but the molecule all the time is moving. Okay, and there is a chance that this molecule will collide with another molecule. And what will happen if you get a collision between them? So let's put it this way. We have carbon attached to another carbon, and here's the third one. Terminal hydrogen, terminal carbons, they have 3 hydrogens. And the one in the middle, it has 2 hydrogens. Okay, now I'm going to draw this shape around it. Okay, so let's say this one is moving and collides with another molecule. Okay, so what will happen if we get collision between them? Or, you know what, for temporary, like a really short time, for short time, you know, the electrons somehow they move to one side of the molecule. Okay, the electron kind of they shifted to one side of the molecule. In that case, okay, in that case, you will have a positive pole and positive poles and positive and negative poles. So either because of the collision or you know, really in a short time, electrons move to one side. It doesn't matter, like it doesn't matter which side. So I got this. I got an even distribution in electrons. So let's say we got negative charges here. That means the electrons happen to be on the right side. So what will happen on the left side? I'm going to have some positive charges. Okay, so here I got negative charges. There we got positive charges. Okay, can I have such a distribution inside another neighbor molecule? Yes, it can happen. Okay, and now what will happen if these 2 molecules see each other? They get close to each other. Now we will have positive charges facing to negative charges, and very soon we're going to get interaction between them. This interaction, because it's really short, okay, the time or half-life time, okay, or lifetime, okay, lifetime is really short, okay, it's really short, okay. So because it's really short, you're not gonna get permanent positive and negative charges. So how about this? Let's call it temporary, okay? Temporary positive and negative charges. Your molecule is non-polar, but in a short time, okay, in a short time, I got positive and negative charges. So again, the lifetime is really short. It's really short. Okay. Because it's really short, you can't have those positive negative charges forever, and that means the dispersion force or the force that you get, it will be weak. So the dispersion, the forces that we call it dispersion force. Okay. Dispersion force is different than dipole force. Okay, and why is different and why is weaker? Okay, because the lifetime. Okay, because of the lifetime. So I'm going to say dispersion force will be the weakest force. Okay, it's weaker than dipole. And the reason for it is just because of the time, the lifetime for it. Lifetime is really short. Well, the dipole is permanent. And the strongest one, it will be the hydrogen bonding.